Next, we have Steven Samoil on behalf of Dr. John Chen, who couldn't attend today, to make his presentation.
Okay, hello everyone. As you heard, I'm presenting for Dr. Chen as he's unable to make it today. I'm Steven Samoil and I'm one of his PhD students at the University of Calgary. What I'll be talking today is a bit of an update on our research group as well as reservoir simulation based on physics-informed spatial-temporal machine learning. So a bit of an outline of what I'm going to be talking about. The energy simulation, or NSERC energy simulation research chairs research that we've been doing. The current status of our artificial intelligence and machine learning in reservoir simulation, as well as getting into a specific topic of physics-informed spatial-temporal artificial intelligence and machine learning, and then looking at a few examples of artificial intelligence-based reservoir simulation. So the overall research goal of our chair is the development of a reservoir simulator and trying to advance that as far as we can. We have, in the current term, been addressing this through three different prongs of attack. The first is to study steam and steam solvent injection processes for oil, specifically heavy oil and bitumen recovery. We're also looking to incorporate artificial intelligence and machine learning into reservoir simulation, as well as looking at use in other areas such as geothermal energy and carbon capture, utilization, and storage. So to give a bit of a brief history of numerical simulation, to give some context to how we're integrating the machine learning into our processes. Back in the 1950s, we started with fluid flow and porous media, so that was kind of getting to the very beginning of things. And then we got into the standard black oil simulator, with the next progress being towards compositional and thermal simulators, and then eventually chemical simulators. So we've been advancing the behaviors that we've been able to model through a lot of the simulations. And to be able to further advance this, we believe that the best way is to start integrating the artificial intelligence. The different aspects of the simulator that we work with is we start with the data collection to start developing our models. We then look at getting data from the field, from different lab tests, and then actually developing the various different models that can describe the behavior that we see in a lot of these experiments. So, one of these could be the standard black hole model, or getting into much more advanced models like compositional simulators. One of the big focuses of our research group is trying to make our simulator as parallel as possible. So we've been trying to focus on getting things onto as large-scale compute clusters as we possibly can. I'll go a little bit more into this in the later slides. And then a key part of this is also getting into the analysis, and this is where we'd also like to start integrating a lot of the machine learning. So as I said, we're starting to see much higher requirements from the development of detailed reservoirs. So we're getting into much higher resolution reservoirs. So we're getting into very, very large scale, or very, very detailed, or even very large scale and very detailed reservoirs. And we're trying to increase the performance and the intelligence of our simulations so that we get better solutions. We're trying to get into as large-scale performance simulations as we can. So we're starting to get into models. One example that we've got results from here is one that has 3.5 billion grid cells. So we ran this on one of the big compute clusters in Canada called the Cedar cluster. We used 360 nodes on this cluster, which means that we were running it on anywhere between 2,800 and 5,800 CPU cores. And we still found with a model like this, it was still taking us at least, well, it could be at minimum 10 hours to solve these models, which means that we do need to hopefully find ways that we can improve the performance and the accuracy of these simulations. So a bit of the history of the machine learning that we've been working with, and machine learning in general. So a lot of these techniques have been around for a very long time. Neural networks have been around since the 1950s, and then we've seen a steady advancement through other methods because neural networks were not actually tangible to be used until very recently. So we see things like nearest neighbors, decision trees, getting into reinforcement learning, and then starting to advance towards recurrent neural networks, generative adversarial networks. And then with the biggest, latest development that we've seen, we're starting to see transformers. So these were originally developed by Google in 2017. And a lot of people are probably aware of these now as integrating into things like ChatGPT. So they're quite advanced in the models that the behaviors that they're able to reproduce and model. The growth of these transformer models has been exceptional over the last little bit. In 2018, it started with 130 million different parameters that they were training in these networks. And even just less than a year later, they were already training 1.5 billion parameters. And we're seeing with the latest models that they've been released, we're getting into the trillions of parameters just to model the behaviors of these complex relationships. So we're hoping that with some of our research, we can really take advantage of this advancement. There are really three different ways that you can approach solving these problems that we're looking at with reservoir simulation. So you can go on the traditional side where you're purely physics driven. So here you're using the actual mathematical relationships, the equations, the PDEs to simulate the behavior of the reservoir and the fluids that you see in it. And this is what we would call a transparent box, and it really requires no actual data to run the simulations. We just use models that have been derived from behaviors. The other end of the spectrum is the big data. So this is where it's a fully black box model. You throw a ton of data at, say, a neural network, and you hopefully model the behavior without any much input from the actual reality of the situation. What we want to do, and what seems to be the trend, is where you can work with a limited amount of data. So you can work with a smaller set of data, and you really start integrating the physics of the problem into it. So you're starting to look at a gray box approach, where it really considers the actual physics of the problem, so you don't let it get away from you into edge cases. So what we're finding is what we really want to do is we want to take advantage of a lot of the big data techniques that have been out there in the past, and we're working with a lot of very, very large data sets and very large reservoir models, and we're starting to apply the artificial intelligence and the machine learning to try and extract complex relationships and complex patterns in data that may not have been possible to bring out with any other different methods in the past. When you start looking at machine learning techniques, there's several different approaches that you can look at, and we've been using all of these different approaches in our work. The very classical methods would be supervised machine learning, where you label every single piece of data in your data set with whatever class that you want it to be classified as. So you go at every data point, you say this belongs to this class A, or you go to this and it belongs to class B. It's very time consuming to prepare the data, but it does give you very good results. Or you can take a fully unsupervised approach, which doesn't require any labeling, and it just automatically iterates across the data and is able to define all the different classes in the data and find the results without any interaction from the human other than just starting the process. What you can then do is you can actually, if you're working with very large data sets where it's just not tangible to label all of your supervised data in the actual training, you can actually look at semi-supervised. So you label some of your data and then let that extrapolate out to the rest of your data by using an unsupervised technique. We've also been trying to use reinforcement learning. So this is a very different approach from traditional supervised and unsupervised machine learning. With this, you try to train the data or get the data to train itself and get your model to train itself. So you have some sort of reward for this agent that you run on the data. So you define an agent that is supposed to be modeling the data, and you update it based on some sort of reward if it gets something that's closer to the result you're looking for, or you penalize it if it's getting a result that's further away from the result that you're looking for. So we've been integrating a lot of these different approaches across our reservoir applications. So we've actually been working with methods of applying this to exploration. We've applied it to production, various different tasks within the pipeline area, as well as emerging energy techniques, emerging energy, so new energy, and carbon capture, utilization, and storage. So to look at the reservoir characterization and description, we have a couple of works that are kind of a good example of this. So even back in 2013, we were looking at a hybrid framework for reservoir characterization using data mining, fuzzy ranking, and artificial neural networks. So this we were really trying to improve and speed up the whole process of reservoir characterization. We've also looked at a comparison of various different machine learning methods for estimating permeability and porosity of oil reservoirs by using the petrophysical logs. With this, we actually were able to get extremely good matches with the permeability and the porosity by using machine learning, different machine learning techniques. So the other area that was a very big interest to our research group is reservoir simulation acceleration, so trying to improve the actual process of reservoir simulation. So we've taken a few different approaches to this. We've been looking at trying to actually find or apply it to the solution of linear systems. We're trying to also use it to actually find solutions to nonlinear systems, as well as looking at the phase package calculations and history matching optimization. So one of the examples here is artificial neural network assisted two-phase flash calculations for isothermal and thermal composition simulations. So we actually found quite good results here in this one as well. Production prediction is an area that our group has been quite focused on in addition to everything else. So practical applications of data-driven modeling approaches during water flooding operations in heterogeneous reservoirs. We were using a lot of data processing techniques to try and model this operations. We were applying a lot of this for performance forecasting, specifically data-driven modeling for polymer flooding in heavy oil reservoirs. And we've also been looking at trying to integrate data-driven models for a dynamic prediction of SAGD production performance with field data. So here we're trying to really integrate the real-world field data into these models by using machine learning. And with the trend and the focus of the talks that we're talking about today, we've actually been looking much at a lot of geothermal energy and pipeline defect detection. So we've been applying or looking at a comparison of data-driven enhanced geothermal systems forecast modeling. So here we're looking at specifically a geothermal field in China and trying to forecast the behavior of those fields. We've also been applying thermoeconomic optimization of an enhanced geothermal system. So this one, we used machine learning and differential algorithms to try and figure out the best way from an economic perspective and also a thermal energy perspective to work with that. We've been doing forecasting of pipeline safety as well, so trying to detect defects in pipelines. And we've been doing this through applying machine learning and actually finding quite good results that were much quicker in getting a result from the machine learning method than the traditional methods. And similarly, we've used XGBoost, which is a gradient boosting method to predict pipeline or prediction of the safety of pipelines. So similarly, we were looking at trying to find defects within the pipelines. So moving on to, I guess, more of a specific example of what our research group is working on, we're looking at physics-informed spatial-temporal artificial intelligence and machine learning. So for this, we're looking at trying to use a neural network to model the behavior of the PDEs, and then also applying a physics-informed portion of this, where we look at the behavior of the network, and then we really bring in boundary conditions and initial conditions to constrain the outputs of the network. So we're no longer getting unexpected outputs that don't match physical reality from our networks. So it's trying to use a lot of the data-based modeling and then bring in physical constraints so that it gives us results that actually are usable. So what we've found is that there's actually a lower dependence on the data and then a higher noise immunity than purely data-driven methods. With these specific figures, I can always answer questions later on these ones and pass you along to Dr. Chen as well as the researcher that did this work. One problem that we have discovered is there is a little bit of a limited treatment in discontinuous and non-differential variables. So these functions and these neural networks are very good at modeling continuous behavior, but there are, as you can see here, a little bit of error from discontinuous functions. We've also been trying to apply deep convolution encoder decoders. So with this one here, we're trying to use a different way to actually encode and decode the neural networks so that they actually start utilizing a lot of the physical constraints of the problem. So we've also been looking at trying to use the incorporation of PDEs, so actually incorporating the PDEs into the physical constraints of our neural networks. So we're looking at training the neural network and then actually bringing in the PDE to constrain how we are training the actual network itself so that the network behaves correctly compared to what we're expecting in the real world. Similarly, we've been using convolution long short-term memory. So this is another method of neural networks that it's similar to neural networks. It allows us to start bringing in a lot of the physical constraints as well from the real-world problems. So to give some examples, this is one case here where we ran a simulation as well as did a neural network-based approach. We found that, as you can see in the figures along the bottom here, there's quite good agreement between the physically informed neural network as well as the simulation results, and we're not seeing a huge amount of error between the two different models. Similarly, here we're looking at a reservoir after fracking. So we're actually trying to model a much more complicated case, and we see that there is still, even with a couple of different approaches to the boundary conditions, we're finding quite good agreement between the simulation as well as the neural network-based approaches. In this case here, we're looking at well displacement optimization. We found that it actually does a quite good job at doing the well displacement placement. So I guess to give a bit of a summary, really the big focus of the work that we've been doing is increasing energy resources. So we're trying to apply artificial intelligence to our simulator and trying to use this to increase the energy resources that are available. We're trying to reduce the capital operating costs of a lot of these projects by having better representations and simulation. We've been trying to enhance enhance energy recovery by having a more accurate prediction of the behavior and trying to bring out new advanced methods that we can model better. We've been reducing environmental footprints by trying to get more efficient production plants. And we're driving energy efficiency, so we're getting more bang for our buck from a lot of the energy that we're producing. So a little bit of acknowledgements. Dr. Chen would like to thank the Reservoir simulation groups, all of the graduated and current students, his postdocs, research associates, his project and technical managers, his administrative assistants, and all of the collaborators from industry and academia. And also I'd like to give acknowledgements to our sponsors. Thank you, and I can do my best now to answer any questions that there may be.
Thank you, Steven. Questions from the floor, anyone?
Okay, my name is Alexandre. I'm from University Federal of Pernambuco, Brazil. And is there any framework or library you're using for developing the machine learning models, and the reason of this choice?
So it depends on which model we're using. We've used a variety of different libraries. I think some of our students have developed some of them by scratch. They've actually developed some of the methods that they're using and implemented them from paper. But we're using a lot of standard libraries, so a lot of the standard Python libraries like TensorFlow, PyTorch, those kind of things. Yes.
Okay, please, name and affiliation, please.
Bill Rawson, Delft University of Technology. I'm intrigued by your comment about challenges from discontinuous, I think it was discontinuous functions. Mm-hmm. Would that be in the reservoir description or in the fluid description? Or could you give some examples of what those sorts of cases would be?
Yeah, so for that question, I probably would have to defer to Dr. Chen. So we'll have to probably pass it along to him to find an exact example on that one. Sorry.
Okay, we'll make sure we capture that one. Okay, another one.
Is this on? Yes. Erik Verscheur, also Delft University of Technology. Thanks for your very interesting talk. I have some experience in my community with seismic. So we are doing the wave equation, and we use pins, similar kind of thinking. And what we see is that it's difficult really to get really uplift in reducing the calculation time. So what is your experience? Are you able to push calculation times down with this physics-informed networks by a factor of 10, whatever, or can you say a number here? Or
I can't speak for the whole group. We'd have to defer to Dr. Chen on that. In my experience, I think with the work that I've done, I found it front loads the calculations. You're doing a lot more training, but once you have that trained, then it's, I guess, a bit more generalizable, and you can have the follow-up calculations and application of the networks a little bit quicker. But for that, I'll have to, I guess, defer more specifics to Dr. Chen.
okay. So do you train basically on a general reservoir, so many reservoir models? So it's a very general network, or you train for a specific model only?
So we've got a variety of different areas that we're actually training. So we have some models that we're looking at full reservoirs. We have some that we're looking at very specific things like, say, like the pipeline modeling. So I guess it would depend on the actual application that we're looking at. I think some of them are fairly specific, and then we have a few other models that are actually quite generalizable.
Okay. Thank you.
Yep.
Interesting.
Thank you, wonderful. Yeah, I found it quite interesting. I've seen people talk about physics-based modeling, and they did no more than a decline analysis on a well, and then kind of make predictions based on that. You talked about using PDEs, actually, partial differential equations, which actually capture the equations in physics. So how actually would you actually do it? You have parameters, and as Hardy mentioned, there's multiple parameters, and how do you confine them, constrain them so that it plugs into the PD and get the right answer, so to speak?
So I would have to, for the exact specific answer on that, I have to defer to the student that worked on that work. But my best informed guess would be, as they're doing the training, they're looking at the error in the training and saying, is this going in a bad direction? And trying to constrain it from that direction.
Okay. All right. Great. Okay, thanks for the talk. Stephen, last minute notice to replace Dr. Chen. Thank you again.